All right, well, thanks everyone for joining us for the December gathering of the Champaign Blockchain Meetup. Joining us today, we have Hannah Rosenberg. Hannah is a cryptocurrency and e-commerce web developer, educator, and economist. She has a degree in economics from the University of Illinois at Chicago and was an early cryptocurrency adopter and enthusiast since 2012. She founded her company Velas Commerce in 2014 and has deep roots in the crypto community. She was the organizer of Chicago's largest blockchain community group for 5 years, the Bitcoin and Open Blockchain Meetup. And she's an educator and just does a lot to just let people know what's going on. Lately, she's been doing a couple things. She's been working on the Lightning Network, which is Bitcoin's layer 2 solution. But she's also been helping to develop a course for Saylor Academy. And that course is called Bitcoin for Developers. And so we asked her to join us here today to talk about her new course, because it's a great way for people who are developers and want to get into Bitcoin to get their feet on the ground and get started. And if you want to get into Lightning stuff, follow her on Twitter and do all the other social media stuff to learn that as well. And we were not going to go deep into Lightning today, but maybe you can convince her to share a few nuggets of wisdom if we have time for that. So I'm going to go ahead and just hand it over to Hannah. So thank you.
Hey, thank you, Al. So yeah, like Adam said, there, been involved in Bitcoin for a long time, and today's talk will just kind of, go over sort of an intro to Bitcoin, kind of touch on blockchain a little bit, and then talk about Lightning. It's just, an intro into what I like to call the mechanics of it. So it's not super technical, but it gets into depth about how things actually work. And then it's, I have a number of different resources that I link to at the end of the slides as well. So if anyone does really want to dive into the tech and really learn a lot about the tech, which I highly recommend doing, then there are a ton of resources at the end to help you out, including the Saylor course that just wrapped up. And that is available via sayloracademy.org, and that is free. So it's quite cool. All right, I will go ahead and share my screen so we can see my slides. Okay, I think you need to enable that for me.
Done.
Here to my slide deck. Awesome, thank you. Okay, so let's go back here. Oops. Hold on. Okay, just got to find the right button. Okay, can everyone see my screen there?
Yep.
All right, excellent. So this is what we're going to go over today: Bitcoin, crypto, and blockchain. Really, I say crypto, blockchain. Really, mostly I'm going to focus on Bitcoin because I am, I don't know how familiar everyone is with the crypto space, but I'm mostly into Bitcoin. I am not what you would necessarily call a Bitcoin maximalist, but what I like to say is I'm a Bitcoin-focused crypto enthusiast. So I am a tech nerd and I am obsessed with Bitcoin and Lightning specifically. And so that's what I tend to focus on. And that'll be the context of this conversation. But for anyone who's, very curious about Ethereum or, Cardano or any of these other things that are going on, 90% of what we talk about here is going to apply to those chains as well. All right. So let's go ahead and dive in. Although Adam already did most of my introduction, I'll just show you here. Velas Commerce is my business. We do Bitcoin and Lightning integrations. We're a dev team essentially. So if you've got some cool app that you want to add Lightning to, and you're like, who can help me with that? Like, we're the people that help you with that. I also work at Lightning Labs, and we'll get into that a bit more. What Lightning Labs is a business that helps help to develop the LND implementation of the Lightning Network. which we can dive into a bit more later. But I work with them and I do developer advocacy. So basically they pay me to go around talking about Lightning all the time, which is fabulous. If you're on Twitter and want to dive into the chaos that is crypto Twitter, you can find both me and my business there on Twitter. And then if you're more of a LinkedIn person, that there is how to connect with me on LinkedIn. All right, so if we can, I'd like to do a little bit of Q&A, kind of get an idea of who I'm talking to and what specific things you came here to learn, what you're hoping to learn. And that way, you know, if it works out, then I can make sure that I discuss the things that you were hoping to get to know. So let's start by just doing a few questions. So these are questions like, what is a blockchain, right? Or how many people here would say they understand how a blockchain works? Maybe just by like show of hands. Anyone? Hey, I know how a blockchain works. I understand blockchain mechanics. All right, cool. Good people, a good amount of people. Who holds some form of crypto? Don't have to out yourself on a recording if you don't want to, but if you're happy with that, say I hold some Bitcoin, right? Because I'm really enthusiastic about Bitcoin. Awesome. Cool. All right, who's made some crypto transactions? So they at least have that experience with interacting with it, right? They've sent their friends some crypto, bought something for Bitcoin, that type of thing. Awesome. Me and my husband just went down to El Salvador for LeBitConf and went over to Bitcoin Beach, El Zonte, and got to, you know, pay for most of the things we did. We got to go to restaurants, buy coffees, take Ubers, all using Bitcoin and Lightning. So that was really fun. All right. And now the more advanced one, who thinks they could explain a consensus algorithm? Not going to actually ask you to do it, but who goes like, I could have a crack at that. I could try to explain to someone what a consensus algorithm is. Have anyone? Cool. All right, we're going to touch briefly on Bitcoin's consensus algorithm. But at this point, I'd be happy to ask another question. Is there anything specifically that you were hoping to learn today, right? Did you really want to hear about, you know, mining, proof of work, how Lightning works? I don't know, Ethereum smart contracts, which we won't dive into too much. But is there anything that someone was really like hoping we might get a chance to talk about today?
Let me just talk about it.
Yeah, go ahead. Yeah.
I was wondering how the Ouroboros system works for Cardano or for Solana.
Okay, cool. Well, it's cool stuff, but I'm probably not the right person to talk to about that. But hopefully, if you're looking to understand about more of the mechanics of what's going on, hopefully this conversation will give you a really solid foundation. So then you can go and, you know, read that blog post online that explains how it works, and it'll all make sense because you'll understand blockchain mechanics is what I like to talk to them, what I like to call it. But since I haven't studied that particular application, it would be the blind leading the blind on that one. So we won't do that. Anyone else?
I have a really down in the weeds question that's bothered me since the first time I read about the blockchain. It's basically, you know, you always see this diagram of one block pointing to the previous block. In my day, what that meant was it was an address. But I don't think that is an address anymore. It seems to be, I mean, I cannot get it explained anywhere, but it sounds like you just know the hash of the previous block, and then you search the list of all hashes to find the previous block. Is that right?
Yes. Basically, what you said is
inefficient.
Well, blockchains are terribly inefficient. So you might be entirely correct in thinking about it like that. But I'm glad you're interested in knowing that, because that's definitely the type of thing we're going to cover here. And I actually do have one of those slides showing blocks linked together. I think I have 2 of them. So definitely we'll go through that. And when we get to that slide, I'll stop and pause too. And if there's something that's still unclear, let's bring it up again and cover it again there.
Great.
Cool. All right, anyone else?
If anyone online wants to put it in the chat, we can look at that too.
Yeah. Okay. While people are doing that, I will roll along here. Adam, I'm not sure if I'll see any chats when they come up. Please do let me know if I missed something in there.
Not a problem. I'll keep an eye on it.
Awesome. Thank you. All right. So briefly, what we're going to cover, and we'll kind of let conversation and questions guide what we do here, but this is roughly the outline of what the slides I've put together today. How a blockchain network makes decisions, basically what I call blockchain mechanics, will be the bulk of what we talk about in the beginning here. How is security maintained in a system with no central authority? This is one of my favorite things about Bitcoin and blockchain, so we'll touch on that. What blockchains do well and what they don't do well. I think it's always very, very important to know, even though I'm all in on Bitcoin and blockchain, and I'm just, this huge Bitcoin cheerleader. I think it's really important to have a good idea of what these things do not do well, so you know where they are actually useful for you. All right, when a blockchain makes sense is along those lines: immutability, auditability, some of the features of blockchain tech. Blockchain scaling. One of the biggest problems with blockchain technology is scaling, because it is horribly inefficient. And then we'll talk about that, leads us into a conversation about the Lightning Network. And then I have some educational resources at the end for anyone who's looking to learn more. So let's go ahead and dive into it. There we go. All right, so to understand blockchain applications, you need to understand blockchain. I think it's so important, especially if you're really trying to, I don't know what I'm such in a Bitcoin bubble these days. I don't know really what's going on out there with the blockchain for this and that and the other thing, but I've been in Bitcoin a long time, and I've seen so many waves of people selling blockchain technology for applications that don't really make sense. So if anyone's running across that, I think it is just so helpful to people to understand what a blockchain actually does, because then you can spot it when someone's trying to sell you an application that just doesn't really make sense on a blockchain. So to understand this, I'd like to start with the original blockchain, which is Bitcoin, and the original use case, which is money. And of course, there are now thousands of blockchains, and it's just blossomed or bloomed into this whole industry. But because Bitcoin is the original, and so much of what is going on out there is based on Bitcoin, I think it's really helpful to start here and to look specifically at the problem that Bitcoin was built to solve. Because I think if we understand what the problem was and why this technology was being built, then that really helps us to understand what it's actually doing. So let's dive into that. And I like to start with a bit of internet history. We probably all ran, typed a URL in wrong, just fat fingered it as we were typing something on the keyboard and wound up getting a 404 error, which is, page not found. And this is part of the, just HTTP error codes, which were written, I want to say 80s, I can't remember. But as these HTTP error codes were being built, there was one that was added in here and reserved for future use, which is error code 402, payment required. And I show you this to give you the context that as soon as, the internet was a thing, while the internet as we know it today was still being built, there were people out there already thinking about putting money on the internet, right? How do we have this protocol for communicating? Can we have a protocol for exchanging value as well, right? How do we make internet money, essentially? So this was, as soon as the internet was a thing, there were people out there trying to solve this problem, trying to put money on the internet. And so here are examples of, there's all kinds of different projects, but here are 4 of the more notable ones that were businesses or organizations trying to create digital cash, trying to create money for the internet. Technically notable here is DigiCash. David Chaum was really notable cryptographer, very technically interesting project, actually got adopted by a couple of banks in Australia, I believe. So had some success. Then we have other projects like eGold and Liberty Reserve, which got into a lot of legal trouble and had all kinds of drama. And then Gold Money, which is still around, but didn't quite turn into digital currency. But I bring this up because they're showing you all these different people were working on bringing money to the internet, but all of these projects had one really, really big problem. They all had the same problem. Here we go. We'll start with that. And that is they were all centralized, right? They all had to be centralized because let's imagine that we have some, big long string of letters and numbers, like serial number, right? And this serial number represents a digital coin. Well, if you have a digital coin and it is entirely digital, well, you can just copy and paste that coin, right? I have one coin, copy, paste, 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 paste. I have 1,500 coins, right? You can very quickly see how this destroys, any sort of monetary system, right? This is essentially instant hyperinflation, right? So it's a big problem, and it's the problem of how do you create digital scarcity, right? If you have something that's digital, but you also want it to be scarce, like how do you pull that off, right? So what all of these projects did, these initial projects, is that they had a central server, right? So you would have one node on here that, let's say this is Alice, right? One of these dots is Alice's computer, and Alice wants to send one coin to Bob over here. But Alice can't send a coin directly from herself to Bob. She has to send it through the central server. And that central server does the job of saying, okay, I'm going to debit Alice's account one coin and credit Bob's account one coin. That way we can keep a track of who has what when. We can prevent people from just copying and pasting money. We've tried to create digital scarcity by having this central server that decides who has what when. Now this works. And this is really the model that most of the internet works on now. You have a lot of things that look like peer-to-peer experiences, maybe when you Venmo someone some money, but they're in the back end, they're not peer-to-peer at all, right? If I try and, Venmo my friend some money for lunch, well, it's got to go through Venmo's central servers and then on to my friend, right? So it's all this very centralized system because we need someone to keep a track of who has what when, right? Well, come 2008, someone or probably a group of people calling themselves Satoshi Nakamoto wanted to solve this problem, right? This is a problem that had been plaguing the digital currency space for a while, because when you have that centralized server, all of these businesses, this one, they had internal problems and they just went under. This one had legal problems. This one shifted their focus. This one had legal problems. You have this central point of failure. And if, something goes wrong at that particular business in that particular office, and the entire system goes down. So it's really hard to, Satoshi wanted to take what was essentially a business and turn it into a protocol. But then Satoshi had this really, really big issue that they were up against. How do you take, the job of a central server of deciding who has what when, and instead come up with the protocol that decides who has what when, protocol that creates digital scarcity, right? This is the problem that Satoshi was trying to solve and did solve with Bitcoin. Now, before we dive into exactly how Satoshi came up with this fabulous solution, I mean, it is inefficient and it's complex, but it's just, I think, stunning that the problem was able to be solved, right? But before we dive into the details, I think it's really important to sort of keep this picture in your head. This is the picture I keep in my head whenever I'm trying to walk through what's happening on a blockchain, is to remember that this is just software. It's open source software that anyone can read. Anyone in the world that has, a computer and an internet connection can download this software, run it, and be a part of the Bitcoin network. So it's really important to start there. There's no Bitcoin business, there's no Bitcoin CEO, there's also no Bitcoin help desk if you get yourself in trouble, right? There's, forums you can go to, but it's really important to just keep this picture in your head. This is just, at this point, all we're talking about is software, free open source software. So let's come up with a particular scenario here. and try to walk through how the Bitcoin network solves this problem of deciding who has what when. So of course, Bitcoin is what we call a cryptocurrency, and it has that name because it makes really heavy use of cryptography. Interesting note, Bitcoin does not actually encrypt any data at all. It makes use of cryptographic signatures, hashes, etc. But it makes really heavy use of, without encrypting anything because everything's public, but without actually encrypting data, it makes really, really heavy use of the branch of math we call cryptography. And cryptography helps us out so much because it allows us to use digital signatures so we can prevent fraud, right? We can prevent someone from, trying to send a transaction when they don't actually own that coin. We can use digital signatures to prove the origin and authenticity of a particular message on the Bitcoin network, that message being a transaction. Right. So cryptography is absolutely fundamental to Bitcoin and blockchain technology, but cryptography will not solve the problem of ordering transactions. So let's imagine the case where we're going to show an example where we have Alice and Bob, and then we'll bring in another player, we'll call him Charlie. And we're going to imagine that Charlie legitimately owns 1 Bitcoin. But Charlie wants to try and cheat, right? He wants to do the copy paste. He wants to try to take that 1 coin that he has and send it to Alice and to Bob at the same time, right? So the network knows that the same coin, the network, when I say the network, this is just computers all running the same software, right? The Bitcoin software. So the network knows that you can't, let the same coin be spent twice. But the network has no idea, right? If it sees 2 different transactions, which one is the right one, right? Does that money go to Alice or does it go to Bob? So if Charlie's trying to cheat and send the same coin to Alice and Bob or, any other number of people, the network has to decide which transaction is the right one, which one's the real one, and which one's what we call a double spend, right? Which one's the fake transaction. So this is the dilemma that Satoshi was trying to solve and that Bitcoin did solve via the mining process. So let's dig into that. First, let's just visualize the Bitcoin network. Here are all of these computers on the network, and these could be anywhere in the world. We could have one in Argentina, one in South Africa, one in Sri Lanka, one in Mongolia, it doesn't matter. These computers can be anywhere in the world. And as long as they have, an internet connection and they're, decent enough computer to run the software, then these just computers anywhere in the world. Also, if you're not familiar, we often call computers on a computer network a node. So if you hear me say a node, all I'm talking about is one of these computers. So let's just imagine this network for the moment. Here it is. Of course, it's thousands, 10,000 computers like this, not just these, but for simplicity's sake, we'll imagine this. Then here we have Charlie, right? And Charlie is wearing sunglasses because he's being sneaky. He's very nefarious, right? He's going to try and send the same Bitcoin to both Alice and Bob. There we go. We have Alice over on that side of the network and Bob over on the other side of the network. And Charlie's going to try and send the same coin. So Charlie legitimately owns 1 Bitcoin. He creates a transaction to Alice and signs it using cryptography, and it's entirely valid, right? It's a valid cryptographic signature. He creates that transaction, he signs it, he broadcasts it to the network. He also, using that exact same coin, creates another transaction, signs it cryptographically, and broadcasts it out to the network. And that transaction is sending that same Bitcoin to Bob. So now we have this dilemma where half the network thinks that this coin is going to Alice, and the other half of the network thinks that this coin is going to Bob, and we have to make a decision. All right, here is where we introduce mining. I won't get into too much of the specifics of it, but we want to get into enough of the mechanics of it so that we know what's happening. I changed those computers because this is, sort of what some of the mining computers out there look like. Of course, I made this graphic like 2 years ago, so this might be outdated at this point, but we changed them so that you know that these are mining computers. A mining computer sometimes looks a bit different because they are computers that have chips in them that are optimized to crunch specific numbers, right? To do specific processes, computer processes. So they look a bit different. All right. So we have miners on the network. And again, because this is an entirely open and voluntary network, anyone in the world who's willing to invest in a mining computer and has an internet connection can be a miner, right? Anyone in the world. I've done some mining. You could if you're willing to buy a mining computer. So what miners do, and it's important to note that they do this because they have financial incentive, right? The protocol rewards miners with financial rewards when they solve a block, when they win a round, which we'll talk about in a second. But what miners do is they sit there out on the network. Like, let's imagine I'm a miner and I see all these different transactions going back and forth. Alice sends one coin to Carol. Carol sends one coin to Diego. Diego sends one coin to Georgia. You know, it's all these different transactions going back and forth. And I see all these transactions and I gather up all of this data into a nice chunk of data, or you could call it a block of data, right? And this is where we get this term block. It is just a collection of transaction data. And there's sort of a cap on how big that collection can be, but we just call it a block, right? So I have gone and gathered a block of data. And now I'm going to try to win some money. And what the Bitcoin software very, very cleverly does, and this is the bit of magic sauce that Satoshi added to this problem in order to fix it, is what the software does is create this competition between miners. So here we have two different miners we can see, and they each have slightly different data. One miner on the one side of the network thinks that Alice is getting this transaction, while the miner on the other side of the network thinks that Bob is getting this transaction. They've probably, both of these miners have seen both transactions, but they've just made a choice. Perhaps one transaction came in a split second sooner than the other. And they're like, this one's valid, that one's a double spend, we're rejecting it, right? So there's conflicting data. And so then the question becomes, does the block compiled by this miner on one side of the network, is that accurate? Or is the block compiled by the miner on the other side of the network with slightly different data, is that accurate? So what the Bitcoin software does is sets up this competition. These two miners then take their block of data and, they race with each other to solve a mathematical puzzle. If you want to know the details, it's a hash. They have to take all the data in that block and come up with a hash that has a certain amount of zeros at the beginning of it, so it meets with the current network target difficulty level. But if that means nothing to you, don't worry about it. The important part is that they're racing with each other to solve a mathematical puzzle. And it just takes a lot of computing power. It's just kind of like guessing, you just have to guess at what, bits of information are going to come up with a hash that, meets the criteria, right? So they're guessing as fast as they can at how to solve this puzzle. And what's really, really, really beautiful about hashing is that it's difficult. You can't really guess, right? You can't look at a piece of data and guess what the hash of it is going to be. You just have to brute force it and try it. And so, but once you get a hash, right? If the miner that thinks Alice has or the miner that has the transaction saying that coin is going to Alice, if that miner happens to come up with an appropriate hash, solves the puzzle, well, they can broadcast that to the network, and it'll take all the computers on the network just a fraction of a second to validate that miner really did win the race, right? So it's a situation where it's very, very hard to solve the puzzle. In fact, even with thousands of computers on the network, it's generally going to take about 10 minutes for a computer to win that race, right? To find an appropriate solution to that puzzle. But once they find it, they can broadcast it out to the network, and everyone on the network within just a fraction of a second can validate that they did indeed win that round of the competition of the puzzle. And so essentially via this competition is how the solution that Satoshi came up with on how to solve the problem of who has conflicting data. basically, as long as the data is cryptographically valid, and there's only one version of, any particular transaction in a block, so it rejected any double spend, you could have, 100 miners on the network with 100 different versions of this transaction from Charlie. But we make a decision because the miner that is first to win the race, to solve the puzzle, is the miner who has the real information, has the valid information, and their data goes and joins the blockchain. So here's where we get to the graph that shows the different blocks. So if we just imagine that this block down here at the bottom is, the block that had, let's say, the miner that had the transaction with the coin going to Alice won, right? They came up with the solution before any other miner. Then they broadcast it out to the network. Everyone was able to see it and quite quickly validate that, oh, indeed, they won that round of the mining competition. We don't have to be confused anymore. That coin is going to Alice. Now Charlie's going to have to explain himself to Bob, right? And then we all move around to the next, we all move on to the next round of competition, right? And going back to the question we had at the beginning about hashes and chaining blocks together, what you do is that hash for the block that was the solution to that puzzle, that gets included in one field in the next block. So every block of data has the hash of the previous block. And this is done just so that you can't have someone show up, a week later and be like, oh, look at this data you forgot about. Here's this block that gives me 100 Bitcoins, right? I'm just going to say, here, add this to the blockchain. And so when they're all chained together using cryptography, then if someone tries to send you a version of the blockchain that has, a false block in it, well, the math isn't going to add up, right? It just because they're all chained together cryptographically, mathematically, right? If someone tries to add false information, the math isn't going to compute. It's not going to add up. So this is done to prevent fraud. And because so much computing power has gone into solving these puzzles, I mean, it gets a bit complex, but this is sort of the security mechanism that if someone wants to falsify data in the blockchain, they have to have more computing power than the entire Bitcoin network, right? Or 51%, you can argue about this, but they just have to have this epic amount of computing power, which just isn't feasible, right? So this is how you get the security.
We do have a quick question.
Yes, now is the best time for questions. I think I have, there we go. Let's do questions.
Oh. Yeah, so I have a quick question. So after the block gets published to the blockchain, you said that the miners in the rest of the network can verify this transaction in like a fraction of a second or something like that. What does it mean to verify that blockchain transaction after the miner has already won and published their block to the blockchain?
Great question. So we need to talk about verifying two different things. First, verifying transactions, and then verifying that a block, right? Verifying a block did indeed sort of win the race. So all nodes, all computers on the network are always validating transactions. That means every time a transaction shows up and pops up in their information, they will go through and look at the digital signatures on there, look at the history of the other transactions they're referencing, et cetera. So every node always validates every transaction. And so if I send a transaction that's just complete BS or doesn't have a signature on it, that's just, whatever computer sees that, it's going to go, what? That's nonsense, and won't even broadcast it to the rest of the network. But if the transaction shows up and they go, yep, tick, 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 that checks out, then they continue broadcasting it to the rest of the network. And this is how transactions propagate through the network. So everyone on the network is always validating every transaction. The particular type of validation that we're talking about here is for blocks to determine who won that round of mining, right? That mining competition. And so in that particular case, it's the hash, right? All that data that's in the block, including the hash of the last block, gets run through a mathematic formula called a hash, and basically it produces a unique ID. And the competition is to come up with that ID, that hash, which matches a certain format, right? And so it's really, really difficult. You can't guess, what a hash is going to be. Miners just they mess with the field of data called a nonce, just adding random numbers to it to try and come up with a hash that meets that certain criteria. But once you win the competition, you can take your block, you can take your winning hash, broadcast it out to the network, and then it takes just a fraction of a second for the other computers on the network to look at that hash, see the data, run through the same algorithm and go, oh, yeah, that's the right hash and it matches the criteria. Okay, they win. Is that a bit clearer for you?
Yeah, it's a bit clearer. Just to follow up real quick. So you're saying that at what point do we consider a block validated across the entire network? Does everyone in the network have to validate that transaction? Or is there a certain percentage before it's like generally considered accepted?
Question.
Great question. And we could get really in depth with this one. But essentially, once it's been broadcast, if you're running a Bitcoin node and it sees someone say, hey, I found the winning block, and it crunches those numbers and it's like, oh yeah, that hash matches, that's the winning block. Your computer, your node will consider that done, sorted. Now you can have weird edge cases where maybe two miners come up with a solution at nearly the exact same time, right? And then there can be a bit more confusion on the network. But this is very rare. And when that happens, it's just that the next round of mining will determine the winner. So then you come up with like a very brief fork in the network. And then the next round, like either this will keep building on top of this fork, or we'll keep building on top of this fork. And the next round will determine that. So it's really complicated. You're like digging right into like the science of consensus algorithms. But essentially, you can just think of it as once someone finds a solution, 99.9% of the time, they just broadcast it to the network and that's a done deal.
Okay, thank you.
Cool. All right. Other questions
Marty,
at this
go ahead.
point. And this is the point where we should have a ton of questions. So let's go. Yeah.
When the winning miner sends out the block to the other miners, and one of those miners looks at that block, takes the hash of the block and sees that that makes sense, how does it know that the individual transactions are true? Maybe that winning miner made up all those transactions, and maybe it had a store of those transactions so that it knew it was going to win. Why would the other, do the other miners all check each transaction to see that he's not cheating?
Essentially, yes. So every miner, every node on the network would have kind of what we call a mempool, which is a little database of all like the currently valid transactions floating around on the network that aren't yet included in a block. So when that block shows up and it has that winning hash, it would look at it and go, all of these transactions are transactions that I have in my mempool and I know are valid. And it would go through and check that, and your computer thankfully can do that really, really fast. And it goes, yep, everything checks out. We're good. We're moving along. So yeah.
Yeah, go ahead.
So I'm at the end of the table from the microphone, so can you hear me?
I can, yes.
Okay, so using your example, I may have missed something, but Alice made the first transaction. Bob copied that transaction.
Kind of. So, well, not exactly.
So my question is, when it gets to the network, say, whichever one was copied, say their network was faster than Alice's network, or the route that it took, how does the network identify the difference between the two identical transactions? The one's valid, one's
Okay.
not. Did I miss
Yes.
the answer there?
Great. Kind of. We went over it, but I'll try reiterating it here. So first of all, it's Charlie that's trying to cheat, right? Charlie owes 1 Bitcoin to Alice and owes 1 Bitcoin to Bob. He's trying to spend the same Bitcoin to both of them. So he makes 2 transactions. Both are entirely valid, right? He can indeed spend that Bitcoin to either one of those people. It's entirely valid. But he, sorry. All right, so Charlie signs both of those transactions, broadcasts them at the same time. Both of them are entirely valid Bitcoin transactions. The only question is which one does the network sort of see first or decide, right? The network has to come up with a decision. And the way in which the network comes up with the decision is by, mining computers on the network will wind up just picking Alice or Bob. because of whatever they just happened to see first. And then whichever miner wins that competition, wins that race, that's then determines who gets the money, which transaction is valid and which one is rejected. So it's this mining competition that solves that problem.
And I think, and Hannah, you can tell me if I'm incorrect on explaining this, but I think another way that you could also think about this is if Charlie wanted to be really sneaky, he might not broadcast those transactions to the entire network. He might broadcast his transaction to Alice, just to Alice, and he might broadcast his transaction to Bob, just to Bob. Now Alice passes on the transaction to the rest of the network, but her connection is slow. Bob passes on that transaction to the rest of the network. His connection is fast. Now Bob has a head start where everybody on the network sees that transaction, so they all recognize it immediately and put it in their mempool. While Alice, because she was slowed down, when everybody else sees that she's telling them that she had a transaction from Charlie, they all reject it because they already have Bob's in the mempool. Is that a reasonable explanation too?
That's entirely plausible scenario. And this is why sometimes if it's a transaction that's really worth a lot or something, you might want to wait for what we call one confirmation. So that in that case, if this was a large amount of money and maybe Alice, this isn't like her bestie, she doesn't really trust Charlie, she might see that transaction might pop up. Well, essentially it's kind of accurate because wallets don't really on-chain transactions, wallets don't really directly talk to each other. They just talk to the network. But theoretically, Charlie could find a way to, broadcast this transaction just to Alice. But if Alice were concerned, or this was a lot of money, right? Maybe she's at the store and she's about to let Charlie walk out with a giant big screen TV or something for this Bitcoin transaction. She might say, hold on, let's wait a second until we get one confirmation on the network. And what one confirmation means is that that transaction is included in a block. So if this were the case, and Alice said, hold on, Charlie, let's just wait one confirmation. Well, you don't know what's going to happen, but odds are that that transaction would go to Bob instead. And so after a while, after about 10 minutes, instead of Alice seeing, that she has one confirmation on that transaction, she would just see that the transaction is invalid. She would see an error, right? And so that's how she would know. Yeah.
Just a brief follow-up from a person pleading ignorance here. If I were Charlie and I was going to be Charlie the cheater and send it out, wouldn't it be in my best interest then to just make sure is the blockchain assuming that the first transaction is always a legitimate coin? Because if I were Charlie the cheater, I would just send the faulty coin or the non-legitimate coin to the second, third, and fourth person.
Right. So again, this would be really technically difficult to try because you don't send transactions directly to a wallet, you send it to the network. But theoretically, yes, what all these different nodes and miners on the network are doing is they're just going to take the first one they see, right? And if they see a duplicate of that transaction, they're going to reject it as a double spend. So yes, it's kind of the first one that comes in. Yeah.
If there's a crime committed, though, it's not the first transaction, it's the second transaction. Charlie is breaking the law the second time, not the first time, right? The first one's legitimate.
Yes.
Exactly.
One is the problem. And so if the network can validate the second one before the first one, then how does the network?
Well, I mean,
that's the problem. They can't tell the difference. So
if you think about it, you don't necessarily assume that the second one's the issue, because what if you wanted to send the second one as like the legitimate one, right? So whichever one, it's like both of them have an equal probability of being like right.
It's like quantum mechanics. Until you make the measurement, you don't know.
But Charlie is
Schrodinger's Bitcoin transaction, yes.
So the fraud is on Charlie.
Right. But Charlie's technically frauding both of them.
So Charlie's
right?
the one attempting to commit fraud. Yes, and the blockchain, is not going to be fooled for more than about 10 minutes, right? It's going to reach a resolution on that. It's like basically that's like the court. The blockchain is the judge you go to solve this and decide who gets the money.
And could the network decide that the second transaction, the first transaction is the right one, even though it came in second time-wise?
Well, the network has, no understanding of this, right? It doesn't, it only knows valid or invalid and which one gets included in a block. So the network doesn't know that, Charlie was trying to defraud Alice, right? It only knows valid or invalid and which one gets included in a block. And so that's all it's going to go off of.
It's
I
like,
thought I understood this before, because I've been paying attention, but I thought I understood this differently than you just explained, so I'm changing my process.
yeah. It's like writing checks, but, the network is determining what order to cash the checks. It's very, almost instantaneous.
The network doesn't care which one is true, it just wants it to be consistent. Which one ends up in the block?
The network has no idea what's going through Charlie's head and what he did or did not intend to do. All it knows is this cryptographically valid and did it get included in a block? And there can only be one version of it in a block. That's the only thing it knows and the only thing it cares about. And, what Charlie did or did not intend to do is between him and whatever deity he may believe in. So yes.
So what I'm confused about is, does this process only get kicked off when you engage in double spending, or does this always happen? Like, could you run through an example of this where double spending is not occurring, where someone's just making a regular transaction? So you said that
this exact same process will happen even if there's zero fraud, right? This is the process that we go through to, cement new transactions, new blocks into the blockchain. So this process happens every single time. And go ahead.
Sorry, what I was wondering is what are the miners competing over if they're not trying to verify two separate transactions?
So miners get rewarded. They get rewarded with, go ahead. Sorry, we have a bit of a delay.
Yeah, so what I was wondering is, like, in the example of double spending, right? Miner 1 is verifying one transaction, while miner 2 is verifying another version of that transaction. Whoever wins gets to publish their block to the blockchain, right? And there's two differences there.
Correct.
In the scenario where there's no double spending, let's just say I send cryptocurrency, I buy an NFT or something like that, right? What are the two miners competing over?
They're competing to get the block reward. So the miners get to receive all of the transaction fees that took place in those transactions. And in the case of Bitcoin and proof of work mining, they also get a reward where the algorithm just gives them new Bitcoin every time they solve the puzzle for a block. So they're competing, they're monetarily incentivized to, engage in this competition and win more money. So that's what they're trying to do. But you could have two miners that essentially have the exact same data in each block, and they're just racing each other to get the reward. But this architecture is necessary to avoid fraud and to avoid double spends.
Thank you.
Let's move on to some of the other stuff I had, because we only have 10 minutes left here. Go ahead.
Hannah, is Charlie ever held accountable? Right.
Oh, you broke up there. Is Charlie what?
Charlie's not held accountable by the blockchain. He's only held accountable by the person he doesn't pay. There's the consequences that the person who doesn't get the transaction.
Right. In this particular scenario, either Alice is going to be very mad at him. Yeah, either Alice is going to be very mad at him or Bob's going to be very mad at him. And perhaps in whatever jurisdiction they're in, they would engage in some legal action if Charlie actually did succeed in fooling them, which he probably wouldn't, because this would become very quickly apparent on the blockchain. So, because it works pretty well and pretty quickly, Charlie's probably not getting away with this at all. But were he to somehow in some edge case, manage to fool Alice or Bob for a couple minutes and cause some damage, then the, justice for Charlie would have to happen at that local jurisdiction.
So this comes down to, if I owe you $10 and I owe you $10, I've only got $10 in my account. I send you each a check for $10. You get to yours first, you deposit it first. You're out. And I just have to deal with you. You're
yeah, I just walk away. I'm fine.
There. Now, if we could just stick with examples like that, I'm with you.
Yes, it's obviously technically what's going on in the background is a lot different, but from that user perspective, yes,
Sure.
that's accurate. Yeah.
And that's why big transactions will
Okay.
make you wait 20 or 30 minutes to see several blocks clear before they'll count you as being cleared. with them.
What's that?
Exactly,
threshold?
just to make sure no one can try and temporarily fool you. Yeah. You got it. Okay, I think my connection's struggling a little bit here. Can everyone still hear me okay?
Yep.
Yeah.
Okay, excellent. All right, so now that we hopefully all understand a little bit what's happening with the blockchain, this is essentially, that is the proof of work algorithm. That's the proof of work consensus algorithm. There are now so many other consensus algorithms of proof of stake and delegated proof of stake, and I haven't even dug into this avalanche thing. I mean, there's so many different versions of it now, but this is the foundations of it. This is what created, the industry, the science of consensus algorithms, right? So hopefully you all now have a really good foundation for understanding what's happening in the blockchain. Let's quickly go through that and take a look at what that means blockchains are good at and what they're really bad at, just to we'll go through this really quickly, but just so we have a rough idea of how to apply this. I always like to say blockchains are built for sharing and agreeing upon data with people you don't know and you don't trust, right? So if you want a system where we're all agreeing on what's going on, but we don't want to have to trust a central authority, that's where a blockchain is really handy, right? What's also really neat about on-chain, any transaction on a blockchain, is that they're cryptographically signed entries, right? So you can't lie about whether or not you sent that transaction, right? If you have been recording blockchain data, or you have a node that was keeping a track of what was going on, then you could go to court, if Alice got, duped by Charlie, and she could be like, look, he sent out this transaction to me intentionally, fraudulently, because look, here I have the cryptographically signed transaction. It's proof that this came from Charlie because it's using his keys, right? We won't dig into cryptography here, but this is one benefit of doing things this way, is you have cryptographic proof of who did what when. Immutability. What happens in the blockchain is essentially written in stone, is the digital version of written in stone. It is infeasible to go back and change the history of what happened in a blockchain, right? So we're not going to say entirely impossible because, like quantum computing, or if aliens showed up and have really powerful computers, there's some sort of strange, really weird edge case we can imagine, but essentially it's never happened. And in my lifetime, probably will never happen that someone can go back and rewrite a blockchain. All right, auditability. This applies only to on-chain transactions, but because everything is entirely public and not at all encrypted, entirely public, entirely open, everything that happens on a blockchain is entirely auditable, which is why some like charity groups will start using, blockchain transactions so that you can see where your money's going, et cetera. All right, we're not going to dive into public versus private blockchains because we don't have time, but this is the graph I used or the picture I like to use here, because these are very, very different animals, right? So we'll come across that. Maybe at some other point we can dig into that one. Couple problems when it comes to blockchain in business is that, if you try and, for example, use a smart contract to control something in the real world, or, to make a bet about something in the real world, you can often fool these systems just by feeding it bad data, right? This is called the Oracle problem. It's a very big problem here. It leads to the phrase garbage in, garbage out. A smart contract's only as good as the data you give it, because again, a blockchain has no idea what Charlie's intentions were. It only knows the data and the math that you feed it. That's all. Blockchains are not databases. Blockchains are really horrible, slow, inefficient databases, especially anything relying on proof of work. Like space in a public blockchain is a scarce and valuable resource. You really don't want to ever use a blockchain as a database. You can timestamp data, but you don't want to store a bunch of data in a blockchain. All right, so blockchain tech is amazing, but it's not magic. And we'll briefly cover one big problem with blockchain, and that is scaling. So we took all of this architecture that I just explained to you, how this whole system works, and it has a really, really big scaling problem because everyone needs to know about everything. That means if I use Bitcoin to buy a cup of tea in the morning at a cafe in Buenos Aires, then every single computer on the entire global Bitcoin network needs to know about that transaction. That is epically inefficient, right? And this is a big problem for scaling blockchains. We look at often transactions per second. I put these numbers together a couple of years ago, so they might be outdated now, but just to give you a rough idea, you could say the network can currently do 3 to 4 transactions per second, maybe 7 transactions per second. We can compare that to Visa, which currently doing like 1,700 transactions per second, and theoretically could do like 24,000 transactions per second. You can see there's this massive difference in scaling, especially if we're talking about using Bitcoin for payments. So I'll introduce you to, well, first of all, there's 3 aspects of scaling. It's not just transactions per second, it's also blockchain bloat, right? Should everyone be keeping an immutable record of that transaction I used to buy a cup of tea in Buenos Aires one morning? Like, probably not. That's not a very good use of that space, right? So we don't want to put too much silly data inside the blockchain. Also, if you just have too much data going around on the network, if you have so much data going back and forth, there are actual physical limits on how quickly that data can get from here to there. And you're going to wind up with more difficulty in reaching consensus because you're just going to have data coming in too slowly. All right. This is why I will briefly, very shortly introduce you to a concept called the Lightning Network, something I'm very obsessed with. It is a way to do transactions that are not on the blockchain. We call them off-chain. They're what we call a second layer, and it requires only local knowledge, which is why I love it and why I think it helps with all 3 aspects of scaling. Now, to go back to the analogy that we had earlier with sort of the idea of writing a check, well, I often use a similar analogy for the Lightning Network. It's very important to note that the Lightning Network is not a separate coin. It's not a separate chain. It is just an additional protocol on top of the Bitcoin protocol. All Lightning transactions are entirely real transactions. You just create a transaction and kind of just exchange it around with other people on the Lightning Network without broadcasting it to the main network, right? So you can just send it to your buddy without broadcasting it to all the nodes on the network. It is kind of like writing a check, but instead of taking it to the bank, you just pass that signed check around via other people that you know in your community. So let's just watch this brief video, which kind of just shows a real Bitcoin transaction just kind of getting passed around on the Bitcoin network or the Lightning Network above the Bitcoin network. Now, we're kind of out of time. I have time to sit around and hang out for a little bit longer if people want to do questions on the Lightning Network. I don't know if you all have time. Quick benefits of Lightning, near instant transactions, very small transaction fees. You can do micro payments. There's added privacy, and all with no third parties. They're routing nodes, which are like similar to mining type, like in those type of intermediaries, but no major intermediary. So I'll just put up these links here. These are educational resources that I recommend. Again, I compiled this course here, Bitcoin for Developers, which is up on Saylor.org. I think I said SaylorAcademy.org earlier, but yeah, the URL is Saylor.org. That's the course. I compiled that course in conjunction with Andreas Antonopoulos, who of course wrote the book Mastering Bitcoin and wrote the book Mastering the Lightning Network, which is my holiday reading. There we go. Lovely. And I also highly recommend Andreas's website there, especially if, if you want to learn the technical specifics. He, wrote the book on Bitcoin, has great stuff. And if you don't want to learn the technical specifics, he also wrote a book called The Internet of Money, which is from a non-technical perspective, and I highly recommend as well. So we'll pause there, but I am happy to hang out for a little bit longer if anyone has further questions. Thanks.
Thank you. Thanks. Yeah, I think we can open up for a few questions. Go ahead. Anybody?
I have a question about, as the miners are collecting the various transaction requests, they're verifying them, they're adding them to the block they're building. How do they know when it's time to create that nonce and broadcast it to the rest of the network? How do they know when to, when the block is done? Why I mean, I could
Great
be
question.
much faster if I just sent out the one transaction block, right? And then I would win.
Yeah. So what you do is they would sort of, well, the question, well, you're breaking up a little bit, but the question that I heard is, how does a miner know when they have won, right? And the answer is that the software will set every 2 weeks, roughly every 2016 blocks. It will look at what happened in the past 2 weeks and then come up with a new difficulty target. All that means is it changes the format that is required for the winning block, right? The winning hash of a block. And that has to do with the amount of zeros that it starts with. So you have to come up with a hash that has, starts with 5 zeros or 10 zeros. These are really big numbers, and I can't remember what it is today. But a miner will be aware of what the required format is. And as they're crunching these numbers, they'll keep looking at that hash. And this all happens via the software, right? But they're crunching the numbers, trying it again and again and again until they come up with a hash that, meets that criteria. So if it were a program, it would be a loop that looped through, but it's just, they have, they know exactly what the format is, and they just keep trying until they get a hash that meets with that format.
Question in regards to the Lightning Network. Does that sort of act as a mini platform where people are depositing funds or depositing Bitcoin into their own wallet on your network, or how are you able to lower or increase the transactions per second, increase efficiency so much?
Great question. Okay, so we have the Bitcoin network, which is like this 10,000 computers down here where everyone knows about everything. And then you have the Lightning Network, where really only local knowledge is required, but it's very helpful to have links to different people so that you can kind of exchange value between those different people on the network, right? And what happens is that a Bitcoin transaction is expensive because you need to buy the time for everyone on the network to pay attention to what you're doing, right? Say, I have to make the transaction fee valuable enough that a miner is going to pay attention to me, because you're competing with everyone else in the world that's on the Bitcoin network, right? But if you do a transaction that's just on the Lightning Network, it doesn't have to touch the blockchain. So basically, you just sign a transaction. It's like signing a check. It's perfectly valid. You can cash it. You can take it to the Bitcoin network and cash it at any time you like, but instead you can just sort of exchange it around on the Lightning Network. And the fees are so small because there might not even be any intermediary that you have to go through. You might wind up routing a transaction, being like, hey, it's a bit technically more complicated than this, but roughly you can think of it as saying, hey, so-and-so, can you forward this transaction to my buddy over there? And basically you have to pay them, but because you're not going through the mining process, because you're not competing with everyone else in the world for that node's time, that computer's time, then the fee is just like computationally forwarding that transaction on is like not much more difficult than like sending a text message, right? So you're really asking them for such like a small like favor that you can pay just like a fraction of a penny, and they're like, sure, I'll forward that transaction on. Boom. So it's because you don't have to go on the main chain is why it's so much cheaper.
And how would someone get access to that Lightning Network?
How would someone what?
Gain access to your network.
Okay, well, from a user point of view, you just download a wallet that is Lightning enabled, and you'll have to then move some Bitcoin into that wallet, and then that wallet will handle going on to the Lightning Network for you. From more of a technical point of view, you have to lock Bitcoin into a particular address, which is a 2 of 2 Lightning channel. Basically, you have to put funds into a specific type of Bitcoin address that is a channel that then allows you to trade transactions around on the Lightning Network.
Thank you.
So I have a question. So you explained how a blockchain works for finance and stuff like that. I was just wondering if you can give a quick summary of how it works for decentralized apps and how blockchains like Ethereum can host more things than just finance.
Okay, so we're then going into this is a question that my head comes up is, what's the difference between Bitcoin and Ethereum, right? So why do we have all these DeFi applications, NFTs, all this other stuff going on Ethereum and not on Bitcoin? And I have a whole presentation on just that topic, a whole slide deck for it. But very, very briefly, Bitcoin was built for this use case of payments, right? To be money. Then people came along like Vitalik, who wanted to do all kinds of other cool applications on Bitcoin, and was like, Bitcoin just doesn't do this very well. It's very limited in what it does, right? So anyone who's, into computer science, what like Turing complete is, like basically Bitcoin scripting language won't let you do loops, right? You can't write any kind of program you like on there. It's very limited in its functionality, which you can see as a bug or as a feature because it does what it does very, very well. But people who wanted to do smart contracts, which keep in mind they deal with like state a lot more and transitioning state and keeping a track of different things, and they use an accounting system rather than like a UTXO system. Like there's all these technical differences. But if you want to write these you can also think of it as just if you want to write more complex, transactions, more complex contracts, then you go to something like Ethereum because it'll let you write loops. It'll let you, keep a track of different variables and all kinds of different stuff that just isn't available in the very limited scripting that is on the Bitcoin protocol. So that's a very, very technical answer to that question. Is that what you're looking for, or was there something else in there?
Yeah, it's along the right path, I think. I'm understanding it more. I'm just more confused as to like how people can host like apps that are not for finance. Like how does the entire mining process work? How does like everything you explained go into context of like someone who just wants to make like, a simple app? And what does it even mean to have a decentralized app? Like how is that different from a regular app?
Right. So a decentralized application, often what they're talking about is a smart contract running on Ethereum or something like Ethereum. And what you do is you just write some code and then you embed that code in the blockchain, right? So then it's scary from a developer's point of view because you can't go back and change anything in your code. It's now immutable, right? So you just take this code and essentially you put it as a transaction and it gets embedded and stored in the blockchain. And then when someone else wants to interact with it, they call that contract. So they have to pay a lot of transaction fees. On Ethereum, we call them gas fees, right? And that you pay because everyone on the network has to run your code, has to interact with that contract and run that code. So that contract then lives in the blockchain. When you interact with it, when you send a transaction to it, all the computers on the network go and read that code and run that code for you and do the thing and then spit out the answer. And it can be very expensive because you're asking everyone in the world on the Ethereum network to go run your bit of code for you. So.
Do you have like a use case of this that's not for finance?
There are so many different use cases. Self-sovereign identity, like there's the DAO, like this idea of decentralized autonomous organizations. The primary use case was like a crowdfunding application where you can set up a smart contract, which then like issues people like tokens of ownership, which give them voting rights. And then someone can submit a proposal for funding. And then the people who own those tokens can like vote on which project to fund. And because that contract controls some tokens or ETH on the Ethereum the Ethereum blockchain, then it can just count up the votes and then automatically send money to whoever, won that vote on which, what project to fund. So that's a good example of like a smart contract that can run in a decentralized fashion, an application like a crowdfunding application that can run in being governed by the blockchain rather than humans, essentially.
Cool. Okay.
Yeah, go ahead. Hannah, we've talked a lot about proof of work today. Can you give me a quick and dirty overview of how proof of stake and proof of work, what the differences there are?
Yes, I can, but it's just going to be a rough overview because I've spent all day in proof of work land and very little of my day in proof of stake land. But the idea is that proof of stake wanted to get away from proof of work, right? A lot of times it's people who are concerned about all the electricity that goes into proof of work. And there's a ton of debate in the crypto community at large over this, where people say, oh, it's a bug that proof of stake uses so much electricity. And other people say, no, it's a feature. You can essentially think of Bitcoin as being backed by electricity, right? All the electricity that it takes to run it. But proof of stake, whatever you think about all of that, is the idea that you have to get someone to kind of risk something, right? Miners, they're buying these computers, they're, using all this electricity, right? They're sort of, they have skin in the game, right? So how do you get people to do this work accurately, right? So you have to reward them with block rewards, but also what you can do is do proof of stake. So essentially in proof of stake, instead of a miner, you have a staker. They take some ETH that they own and they lock it into like a special contract where they're basically putting that money at risk, right? And then they go out and essentially vote on what is a valid block of transactions. But if they vote to like include a double spend in a transaction, or if they, vote to do something dodgy, then, it's complicated, this technical specifics of it, but essentially if they vote wrong, they lose their money. So you have to have like, the idea is the carrot and the stick. The carrot is the block reward and the stick is, for proof of stake, is the money you're going to lose if you behave badly on the network. So that's proof of stake in a very, very brief synopsis. Yeah.
Just a little bit of follow-up to that, and this is just one of those questions that, I don't know, I've never heard anyone answer, but it's just always been in the back of my head. So we continue to have the halvings, the final, and we've got rewards for mining, and the final Bitcoin is mined. What's the reward at that point for miners to solve equations after it's all out?
Great question.
In the end, and I don't know when that is. It's like 2040 or something like that. But what's the incentive?
2140.
What is
yes.
it?
It's a
In
while.
about 100 years.
Oh, in about 100
Yeah.
years. Oh, I thought somebody had told me it was 2040, and I thought, 20 years is going to be an
That's
issue.
a problem.
So it's,
Yeah.
it's not. It's for another 100 years. We got it.
What happens then, yeah?
But it's still, yeah.
Still get transaction fees though.
Exactly.
transaction
So
fees, they
what
go up.
happens
Yeah.
is I expect that,
Gotcha.
space in the public blockchain will get increasingly expensive via transaction fees. And as the mining reward goes down every 4 years, I think we'll see, a steady growth in those transaction fees, especially as we get more and more people using this technology. So I think that, in 2140, who knows what the unit of account will be at that point, and with inflation and whatnot. But essentially, I think that putting a transaction in the Bitcoin main chain will be a very expensive endeavor at that point in time. And probably anyone who's using it would be using second layers, third layers, whatever they come up with at that point. Yeah.
John, is it fair to say that this is the reason that the people behind finance thinks that the price of Bitcoin will keep going up and up? Because it will allow that transaction fee to go up and it will be worth it. Is that accurate?
Yes. And also the way I look at this is that this is a global technology, right? And we have a very limited supply of Bitcoin, right? There's only ever going to be 21 million Bitcoins. 90% of them are already in existence. So we have a very, very limited supply. And we have a huge, potentially everyone, with an internet connection on the entire planet could wind up using Bitcoin. So you have this massive supply of potential demand, and you have this massive pool of potential demand in a very, very limited supply. And that's why I personally think that while Bitcoin's terribly volatile, I suspect it will continue to go up and up and up in value for a long time. Yeah.
So,
But I am not giving financial advice. Bitcoin's risky. Do your own research,
One more thing, I was thinking, so as time goes on and more Bitcoins are mined, as we get closer and closer to the 100% mark of Bitcoins being circulated, the equations to solve for that hash gets harder and harder, right? It requires more and more electricity, more and more proof of work, right?
Well, in theory, it adjusts.
Oh.
It can go up or down depending on how much hashing power, how much computing power is on the network. But likely it will continue to go up. Yes.
Okay, so in the likely case, is it ever going to be asymptotic in the sense that we don't get to mine that, like, those X amount of Bitcoin left over? Like, the equations are going to be so hard such that, like, we will not have enough electricity, or like the amount of money that is required to make something that big will not be worth it.
Great question. And this is a point of heavy debate in the crypto community. It's my personal opinion that no, that will not ever happen. Because as, people sometimes you see these articles that, I think are just trying to scare you about, the electricity use of Bitcoin. And they're like, if this country comes online and starts using Bitcoin, or if this many more, if the network doubles in size, we won't have enough electricity on the planet to blah, blah, blah. And I think that, we will see an increase, I suspect, in mining power, but I don't think it's going to go like this, right? I think, or let me do it in this direction. I don't think it's going to go like this. I think it'll just increase slowly because I think a lot of the new applications are going to go to things like second layers. They're going to go to Lightning. Also, we do get better at scaling on chain, of being much more efficient about how we put transactions on the chain. So I don't think it's not, more users equal more mining power. It doesn't look like this at all. And I think it's like you're going to get dramatically more users and only a tiny increase in necessary mining power because we get so much more efficient and we have the second layer solutions like Lightning now.
Actually, on that note, you were talking about efficiency. Could you explain actually whether Bitcoin is environmentally sustainable? And I've been reading a lot of things about how Bitcoin and Bitcoin mining specifically has environmental impacts. Do you know anything about that, or could you explain about that?
Yes, this is heavily discussed topic, right? And I can't give you the specific numbers on how much carbon or et cetera. I don't know that. What is absolutely true is that Bitcoin does consume a lot of electricity. This is without a doubt true. But then the question for me becomes, is that a good use of electricity, right? I mean, how much carbon did I just put in the atmosphere when I got on the plane from San Juan to Chicago, right? How much, electricity do you use when you turn on the lights on your Christmas tree at night, right? So no doubt Bitcoin uses electricity. The moral question for us is that a good use of electricity? Also, if we manage to, provide utility and services to people in the world that otherwise didn't have them, is that a good use of electricity? If we then, a lot of the banking infrastructure we have now, goes away and replaced with Bitcoin, like how much less energy is going into driving armored trucks around to ATMs, right? You have to look at, the overall effect in the world. What benefit does it bring? What, electricity use or, carbon use does it eliminate in some places? And so it gets to be a really, really complex debate. I personally find Bitcoin to be a very valuable use of electricity, and I don't have a concern with it, but many people disagree.
And I've been reading some really interesting use cases where Bitcoin mining companies and projects will be basically trying to partner with or maximize opportunities for energy creation. For instance, there are mobile mining rigs that will go out to oil fields and places where methane would be vented, and they will capture that gas and use it to power generators to run Bitcoin mining equipment, which is actually environmentally more friendly than just letting the methane go on its own or just burning it just to burn it without producing anything else. And then
you could make an argument that Bitcoin incentivizes, renewable sources of electricity too. I mean, you could really get into depth. Again, we could spend an entire, couple of hours getting into this one. Yeah. Yes.
You have to consider how much electricity do all the banks and the Federal Reserve use.
But then what's the solution?
Bitcoin is replacing all that service that they do, all their computers and flying around.
I'm just curious about it. Yeah, cool.
So.
Yeah. No, you do.
One more question.
Yeah. Let's do one more question, and then we'll wrap it up for the day. And thank you so much for staying over.
Yeah, no problem.
So this question has to do with proof of work versus proof of stake. So I understand proof of work is built and designed on top of I don't have to trust anybody to participate in this network. It's built on we don't trust each other. That's the premise of proof of work.
Yes.
Proof of stake is attempting to come back to this concept that we can trust the people we're working with. Now, to me, it feels like a weakness of proof of stake to want to come back to that, because it comes back, and you mentioned this last time, the $5, the $5 remedy is you hit somebody with a hammer and you get them
Yes.
to tell you what you want. So doesn't that make proof of stake more vulnerable?
So
than proof
yes
of
and
work?
no. When we say sometimes people call Bitcoin trustless, I think it's more like, I mean, you have to trust in some ways that someone in the world is going to be willing to run a mining machine, right? That there are going to be some people on the network behaving in the appropriate way. What the thing to me is I see this all through the lens of incentives, right? And Bitcoin continues to operate and to grow because it got the incentives correct. It sets the incentives up that anyone participating gets more money by participating honestly than by trying to cheat, right? So that's really how I think of it, is are the incentives correct that the system's going to work? Now, then you look at the incentives for so I think of proof of work versus proof of stake. I think, how have the incentives changed? So you're not really trusting proof of stake nodes that much more than you're trusting proof of work nodes, but you have to say, what are the incentives for the proof of stake nodes, and are they any different? And then you have this problem, people argue, or it concentrates power in the hands of few, because who's going to be able, only the people with the money, with a ton amount of money to stake, are going to be able to earn rewards, but mining machines cost a lot. Like, it gets really complex. And then there's this concept of, incentive structures that are external to Bitcoin, like the resources, the electricity bill that you have to pay. And while proof of stake doesn't really quite have that same external incentive structure, and does that change things? It gets really complicated. I am slightly wary of proof of stake myself. I'm really just keep waiting for Ethereum to finally switch to proof of stake. And then I think we'll get a really big live experiment on how it works. And there'll be a lot of diving into that data when it happens.
I feel like we're in that place where, I think it was Westinghouse and GE were battling for what we were going to use, AC or DC electric, and they would run this big political, not political, but this media coverage of, well, this is going to burn down your house and kill your family, and this is going to blow up the world, and I feel like that's the process we're going through in order to determine where we kind of end up at the end.
And to this day, but now we still use both AC and DC.
That is true, and that's a really good point, Adam. That's a really good point.
It is.
All right, well, I just wanted to hop on and say thank you so much for joining us, Hannah. This has been a absolutely fantastic presentation.
Thank you.
I hope everyone will take the time to check out your course at Saylor.org. We've got it pinned in our description for the meetup. So if anybody wants to check out those links, you can go there, follow you on the socials, and see everything that's going on. And do you have any final words to leave us with?
No, that's it. My computer seems to have froze. I can't stop the screen share, so I can't see you all. Bummer. But no, thanks for having me. Like, genuinely, I like sitting around talking about this stuff is one of my favorite things to do. So thank you for hanging out with me and chatting about crypto today. It was fun.
All right.
Thanks, man.
Thanks again. Take care.